when I was second year undergraduate at the London School of Economics, I was following sort of a technical, let's say, way to my degree called mathematical economics and econometrics. And I was doing real mathematics in the mathematics department and real statistics in the statistics department. And I was doing the first course in mathematics, in statistics, and the first course in econometrics as a second year undergraduate. And the professor, he was actually a professor or a reader in the statistics department, but he was an econometrician. And he gave me these assumptions. And the way you were taught, we get OLS, and then we start deriving sampling distributions about the estimators and talk about properties and all of that. In the statistics department, they were doing all of this. Define a joint distribution, then use the joint distribution to define a conditional distribution, and of course, a marginal distribution. And when that joint distribution is normal, of course, I'm not going to write down the formula for the five-area normal. It's a pain in the back. But this is basic notation. So five-area normal, this is the mean of y, this is the mean of x, this is the variance of y, this is the variance of x, and this is the covariance. In the case of the normal distribution, things are simple. So when we talk about dependence, we mean covariance or correlation. So I was taught that the regression model is basically based on this distribution here. And of course, if I wanted the marginal distribution of xt, it's also normal. And of course, sorry, this is mu2 with mean mu2 and variance sigma 2. Straightforward is that. So I asked my econometrics professor, I said, why are we doing this? He said, well, in economics, we actually have some theoretical information about the relationship between x and y, which of course makes sense. But are these two things different? He couldn't really answer me that question. I went a step further. And I said, when I do regression in the statistics department with a famous statistician, he would say things like, well, these estimators come from the joint distribution of the sample. And the joint distribution in this particular case, it's basically the product of these marginal distributions. So the joint distribution, you basically start with yt given xt by 1. And you say t goes from 1 to n, and that defines the joint distribution. That is the foundation for doing inference. So if I write it down as a function of y, let's say given x, because this is back notation, but that's the way we often do it. So just to simplify, not to write products, you do all the sampling distributions by using this. And of course, this is defined for all yt's and xt's, and it's n-dimensional, so we have n data points. The function is simply this thing where we replace the y and the x with the data and make it a function of theta. This is not a function of theta. This is a function of x and y. So the likelihood function will just change. So if I do it here, for instance, and write down the joint distribution, it would be multidimensional. So I knew that everything revolves around this joint distribution. Estimators, test statistics, predictions, and all of that. So I asked my professor, "You're not using this?" He says, "Yes, we do." I said, "But it's not the joint distribution of the errors that you write down there. It's the joint distribution of the y given x." He says, "Yeah, yes, but it's easy to derive." That was a lie. It's not always easy to derive. And of course, the assumptions here are not a complete set of assumptions. What makes the betas and the sigma square not change over time? You assume more than just that. They are constant over time. But if you're down here, you know, you're talking about constancy of these parameters, and that gives you the theta. So I immediately began asking questions like, if you give me this, can I get to that? And the answer is yes. Just the pure probability theory, if this joint distribution is well-defined. Well-defined here is, it means it satisfies Kolmogorov existence theorem. That's a fundamental theorem of stochastic processes. In the case of linear regression, it does. But the autoregression, it's a variation of that. So when I was talking yesterday, and we were talking about yt minus 1 phi, the joint distribution, it looks like that. You just replace xt with yt minus 1, and suddenly things go astray. So we really, really have to take this seriously. And it's not the error that we care about when we do statistical inference. When we test the assumptions of the model, it's not these assumptions we're going to test. And of course, it says this thing here says the mean is 0. So what are you going to do? Assume the mean is not 0? How does that come up? Epsilon t is unobservable. If you tell me yt is normally distributed, I know I have data for yt. If you tell me it's independent, yeah, I can look at the data. What am I going to look? If somebody tells me the mean is 0, the variance is sigma square, and the covariance is 0, I can say nothing. And a lot of people say, "Oh, well, we have some tests that we also here." You're testing the wrong things. And of course, we don't have a complete set of assumptions here. Even if we could test whether the mean is 0, how we're going to do, people say, "Oh, I have the residuals." The residuals are not the same as the error. So they have different distributions and all kinds of stuff. So I began, as an undergraduate, doing this transferring of assumptions. And at age 20-something, I started writing that green book that Armando has in his office. It took several years, but in 1986, it was out. And the whole purpose was to do exactly this. There were, let's say, 20 different areas in econometrics where everything was defined in terms of error terms, and what I did was to reveal the real assumptions that matter, which are the assumptions about X, Y, and Z that we observe and we can test directly. I thought it was straightforward. People now know what they're assuming. They will be testing them. No. If I don't have to do it to publish, why would I do it? And a lot of times when I hire new faculty, I was in that position many times. I didn't expect a new PhD student to know what I know. But I would say, why don't you test your assumptions? If the answer was, I don't care because the journals don't ask for it. That was a no-no for me. You want to spend 4 years doing modeling, knowing that your numbers mean absolutely nothing? You don't have any better things to do with your life? Yeah, for your satisfaction. Yes, I did a good job with the data, and now I know I learned something out of it. Those candidates, let's say, got my attention. The other ones, I just dismissed. What does it mean? I spent 4 years to do my PhD, but I didn't really care whether any of those assumptions that I impose on the data are valid or not. So this is how I began doing all the things I did. Now this chapter here, 7, is really at the center of all of this. So I introduced new terminology. When the probabilistic structure comes through the error term, I call it a priori postulated model. That's the different thing. And I use different notation so people are not going to get confused. So in this particular case, how do we go from, let's say, these error terms to the real things here? What matters is not the distribution of the error terms. Any way you do it, everything basically revolves around this bivariate random variable or stochastic process, if we want to be precise, because it underlies the data. We want to know that the data we chose actually satisfy the assumptions we are implicitly imposing. And we're going to be revealing those, let's say, assumptions in a second. If you bear with me, I'll go straight to that. Let me get this in. I don't have it here. So, what does it take? Well, the joint distribution is the Z we care about. And of course, the conditional is easy to derive. We have the joint distribution here and the joint distribution here, and we derive the conditional joint distribution. On the likelihood function, as I said, you take that formula. This is a function of theta, but of course, in practice, we give the theta when we do the sampling distributions. We assume either the theta is a pre-specified value we choose in testing, but when we do estimation and prediction, we basically assume it's the true theta that gave rise to the data. That's why sometimes people get confused. It's a function of Z. And of course, we take that formula, plug it here, and we replace the generic Z here with the data, and now it's a function of theta. All the information is there. When we do maximum likelihood, all we need, more often than not, is to take the log of this, because it simplifies a lot of the derivations, and derive the maximum likelihood estimate. Do we need any of the other estimators? We usually do. No, we don't. Maximum likelihood is always, without any exception, superior to any OLS, GLS, two-state least squares, instrumental variables, and all kinds of other things. We use all those things, and I had to learn it as an undergraduate and graduate student. I had a list of 25 of them, because we are lazy and we play games with the error term. When we derive the distributions, we don't do it as we should. We just cut corners. And we replace, let's say, the formula for the estimator, and everything is driven by this term. When we do OLS, that's what we do. But of course, if you do OLS and ignore the normality, how do we derive the distribution? Well, we play with the error term and then invoke asymptotics. As n goes to infinity, this happens. As n goes to infinity is the afterlife. It has absolutely nothing to do with your data in this life. So we're cheating, but we learn nothing. So people who say, I'm going to make weak assumptions, so if I'm wrong, it's not too bad. That's really a bargain with the devil. There's no such thing. The more precise and exact and strong your assumptions are, the more you're going to learn from this data. But you have to test the validity for the learning to take place. So go for strong, let's say, detailed assumptions, which you can test. And of course, if they are assumptions about the observables, you have the data. There's no, let's say, difficulty in testing your assumption. And of course, here, if you do the translations, you don't get all the assumptions, because in this transfer, you also get this part. Now, I use A's here and betas there because they are different. In this particular case, when you actually do it properly, you know what these betas and the sigma squares are. This is what you're picking up. I forgot to write down, of course, the beta 1, which is sigma 1, 2 over sigma 2, 2. So there's no mystery. And this is extremely important. Now, for those who did any statistics or econometrics and they learn OLS, what they don't realize is that your OLS is nothing more than estimating the mean, that this covariance and variance, and then plug in the mean. And I figured it out because in my exams, I had to reproduce this. But I remember this. And then I said, okay, I want the estimator of that. How do I get it? Well, is beta 0 hat. How do I estimate that? Well, it's basically X bar. That's the sample mean. Then I have beta 1 hat, Y bar. So this is actually the other way around. So I have YT, yes. This is XT. And of course, what is beta 1 hat? Well, the covariance. So I get the covariance here. And then the variance of X and the same for the rest. So if you have seen those properly, I assure you, you just estimate or replace the parameters with the estimator, the obvious estimate, the sample mean, the sample variance, the sample covariance, and you're done. But it makes a huge difference knowing what you're doing. You're not estimating marginal propensities to consume and all that jazz that I learned. That's a different issue. Let's get the statistics right, and then we worry about marginal propensities to consume and elasticities and all the rest of it. If I cannot get a statistically aggregate model, those concepts are meaningless. Elasticities and all of that. That comes back later. So this is basically the background to understand where I'm coming from. And now we go to the discussion. So why do we use conditional distributions? That's an obvious question to ask. And there is an obvious answer, but we have to look at it closely. We know we define independence between X and Y when the joint distribution of X and Y, here I don't even have subscripts because you don't need them. And I cover both this and that. That's not really an accident. I can just tell any of these. Either it's over time and I have dynamics, or it's different points in time. So this is the notation here. So I know if X and Y, two random variables, are independent, the joint distribution will be split into the two marginal distributions. They are unrelated probabilistically. Now, what happens if they are not? I still can split this bivariate distribution into two univariate ones. But one of them, and I can do it both ways, x given y, y given x, one of them is conditional. And it was pretty obvious to me that if independence is this, and if I don't have independence, that's the case. That's where you model dependence. Trivially true. So when you have dependent data, either contemporaneously, xt, yt, or temporally, yt, yt minus 1, this is where you're going to capture the dependence. So suddenly conditional distributions become important because they provide the way to account or model the dependence. It's as simple as that. Now, where all these regressions come from? They are moments of conditional distributions. So the regression function is just the first conditional moment, but with a twist. As a function of the conditioning variable. So it's not just a moment, it's a function, because we let xt vary, or yt minus 1, take all its values. So that's how we actually go from moments to functions. The conditional variance, the same thing. It's the conditional variance viewed as a function of the conditioning variable, allowing that variable to take all its values. That's all there is to regression. Now, when I was a student, the normal was the only one I saw as an undergraduate. And that's why people just go straight to the linear regression. Why? How many joint distributions are we do that? And they're always normal. So in this chapter, I made it clear there are hundreds of regression models, and we are yet to explore them. I explored quite a few, by the way. I had graduate students exploring several of these joint distributions. I explored the students' T and a few more distributions. But that's the richness of this particular way of looking and modeling dependence. You don't have to have normality. But if you don't have normality, some of these niceties, like this is linear and that's constant and all of that, change. And that's the main message from the rest of this, let's say, setup. So here, I take a joint distribution, any joint distribution. I don't impose anything here. And I basically say, okay, if I don't have IID, independent and identically distributed, which is the ideal case, but I'm yet to come across an IID data set in econometrics, and I'll pay money for, if you find one, real data. So what do we do if we don't have IID data? We don't want to have an n-dimensional distribution carried around. We need to simplify the modeling. How do we do it? And the answer is conditioning. So what I do here is condition x2 on x1. So let me just, do I have it? I might have it. Okay, I don't have it here. So when I do this, you might not really realize what it is, but you start with the x there and you say f x2 given x1, and then the next one, of course, is f x3 given x2 given x1, and then you go to f x4, x3, x2, x1, and you go all the way to n. So that's what this notation here is trying to convey. So xk is conditional on all the previous ones. Now, why is this interesting? Because this is n-dimensional, and we hate to work with n-dimensional distributions. 2 dimensions is a problem. So n dimensions is a no-no. But if we do this conditioning, suddenly we realize this is univariate and that's univariate. It's complicated, but it's still univariate. So we can work with distributions. Instead of the n-dimensional, we work with a sequence of 1-dimensional distributions. But there is a catch. And the catch is the tail keeps changing and because increasing. So when I reach f of xn, then I have n minus 1, x, n minus 2, all the way to x1. And that's a problem, because each one of those conditional distributions is different. Why? Because the conditioning is different. So how do we address that? And the answer, of course, is Markov dependence. Markov basically says xt depends only on just the previous xt, which is n minus 1. So we go here, and we basically say, no, that's out. And here, those two are out. And here, of course, all these are out. This is Markov dependence. That's why conditioning with assumptions about not everything is basically changing gives us basically bivariate distributions like this one. Because each one of these is just 2-dimensional, but the conditional is 1-dimensional. That's where we are so lucky to play around with these kinds of cases. So I go back, I get rid of the subscripts and go back here. This is the foundation. A lot of times, we don't need this marginal distribution. Now, you wouldn't know that if you learn linear regression with error terms. If you have normality, you're lucky. In that case, and that case only, you can ignore this distribution. But move away slightly, and you have a student seed distribution, which is bell-shaped and has all the other properties, and you can't. Your linear regression, yeah, it's linear, but you cannot throw this piece away. I figured it out at the time. A lot of the professors at the LSE were actually debating what happens. And I realized immediately this importance. Yeah, if you have normality everywhere, you are in the lucky world and you don't have to worry about a few details. How on earth would that help you if you don't have a normality and you use error terms? I mean, all our regressions are driven by error terms. You cannot throw away this. And that's really hugely important. If you move away from normality, things fall apart. So we don't want to learn regression for one distribution only and hope that your data are normally distributed. It really is a bad idea. Okay, so here we are. We want to work with this conditional distribution, and the obvious thing to do, of course, is look at these moments. Why is this so bad? We don't want to carry the conditional distribution. It's a mess. If you write down the bivariate normal, you need half of the board. And the conditional, that's why I use notation. Otherwise, it's just a pain. So can we just use moments? And the answer is no. We use moments, but we make this not a constant, as all moments are, but functions of x and allow x to take all its values. We go from a moment, which is one number, to a function. And that's regression. Now, we focus only on the first two conditional moments, turning them into the regression function and the stochastic function. To make the difference, we call it names. Now, who was the first guy who actually thought of this? It was Carl Pearson in 1894. So this is not new material. This was there. He actually gave the names, regression and stochastic functions. And he went and said, wait a minute, why do we stop at the first two conditional moments? Who says that those two moments capture all the information in the conditional distribution? So he went on and introduced two more curves or functions. The clitic, which is the third conditional moment, and the curtic function. You've never heard of that because we just blinded ourselves and say, oh, regression is two moments. Not necessarily. If I have a skewed distribution, a non-symmetric distribution, I should be worried about the clitic function, the third conditional moment, because it has really important information about the asymmetry. So things are not as straightforward as people think. And of course, as I said before, sometimes these regression functions are sufficient, but a lot of times you just have to bring in the marginal distribution of x. So here are, because just to let you know, you don't have to stop. So R here can be 2, 3, 4, 5, because sometimes you're going to need those conditional moment functions. Now, what I do later on in this chapter is to get rid of the equation that comes from economic theory, the APP, a priori postulated equation, and create something which is purely probabilistic. So when I specify models, I basically condition. This is a conditional expectation, but sometimes you cannot really condition on the value of x. You condition on something more complicated if you cannot throw away the marginal distribution. So this is why you have this crazy looking thing, which is a sigma field plus an error. But this has nothing to do with economic theory. These two pieces are orthogonal by construction. And the error term is not driving anything now. It's just this difference. It's a derived error term. It's not everything else I forgot to put into the regression. Forget that. This is your data. This is your regression. Forget about it. Whether there are other variables or missing things, that's not for this part, the statistical part. If you can get a statistically aggregate model with this, then worry about omitted variables and all kinds of other adjustments. That's not a statistical problem. It's a substantive model. Do I have a complete model? And of course, the first time I came across this I included all the relevant variables in my regression. I laughed loud in class. And because the professor says, why are you laughing? I thought this is a joke. He says, why? And I said, is there anybody on this planet, not just this room, who ran a regression and can tell me that I included all the relevant variables? What the hell is that? And I said to him straight out, if that is an assumption, we should pack it up and go home. It's a silly setup. And I worried for 2 or 3 weeks before I figured out this is really a joke. Yeah, there's no such thing as I included all the relevant variables on the right-hand side. I included what I included. Is it a well-defined statistical model? Yes. So worry about its validity. And when you're done with all of that, start worrying whether you're missing other variables. But don't start worrying about before you do the statistics. Which is statistics, it means the assumptions you make with a given data set or the stochastic process underlying that data set. So that is later on in the chapter, but I wanted to warn you from that. So let's get a handle of what a conditional distribution is. All right. Here is a discrete example because you really need to grapple and understand moments and functions of the moment. So this is x and y. These are the values of y. These are the values of x. And of course, if you sum over rows, you get the marginal distribution of this guy. And if you sum over columns, you get the marginal distribution. This is the integral you saw in the presentation. Here is just one integral to go from the joint to the margin. That's it. But if you have a discrete distribution, you just sum up. Now, you will know you made a mistake if you add these numbers and those numbers and you don't get one. So things cannot really go wrong. So using this, how do we calculate, first of all, the conditional distribution, and then, of course, the regression and stochastic function? Here it is. So remember the formula. You take y given x. For each value of x, you have a different conditional distribution. But you want to do it for all because the regression function has all of them. So we first start y given x equals 1. And of course, is the joint x is always 1 in these calculations. But y changes from 1, 2 to 3. So this is simple arithmetic. You do the calculations here, and then for different values of y, 0, 1, 2, you define the conditional to take 3 different values. So the conditional distribution, of course, here is a function of y. That's the only thing that changes because we nailed down x to 1 value. But to define regression, we need all the values of x. So we do it for x equals 2. So 2, 2, 2 here, the 3 values of y, the same calculations, we get another conditional distribution. And of course, x values the 3 as well. So as you see here, I screwed up in the notation. So it was supposed to be 3, 3, 3, but I did the calculations and made a mistake in the notation. So, but I can assure you, the numbers add up nicely. So I have 3 conditional distributions, each for a different value of y, and now I need to define the regression and the stochastic function. Here they are. For x equals 1, The regression takes this value, for x equals 2, takes this value, x equals 3. So what is my regression function? Well, in this particular case, if I were to plot these things, I have to have y here, x here, and of course, just put those numbers. So this is up to 0.9. So let's make this 1. And I go here and say for x equals 1. So this is 1, 2, 3. The value y equals 0.4. So 0.4 is somewhere here. This is my first point. Do the same thing for x equals 2. It just goes all the way up to 0.9. So that's my next point. And then, of course, for x equals 3, I get something like 7.5. So that's my regression function. Now, to look better, because this is discrete, we sometimes just connect them. But this is what a regression function is supposed to be. Of course, we can do it for the stochastic function and so on. Here, I remind you of exactly what we are doing when we are talking about stochastic functions and regression functions, not only for r equals 1 and r equals 2, but in general. So this is just a general way of doing. And I want you to remember, if you don't have normality, you might have to go to these higher conditional moments and the functions that go with it. So here are the formulae, but as I said, I had to go to the third only once. And of course, what I do here is define, and this is how you're going to report it. Your regression function is this, your stochastic function is this, you need this, and also you need the numbers inside, as I did on that plot. Now, if life is generous and we have normal random variables, and they're also independent in a certain sense, then we are in paradise. And this is what happens. It's a continuous distribution, which means we have very simple and straightforward functions. This is reminding you that if you have a joint distribution, you also know what the parameters represent. You don't have to guess. You know. In the derivations, you really get the whole thing. And this is the case for all the normals. Now I go to the clinic and curvature functions because I know at some point you might want to get into that. So the reason why the bivariate normal is such a nice thing is because it's characterized by its first two moments. Not only the marginal, but also the conditional, and of course the joint. You don't have to worry about anything beyond the first two moments. But if you do, here are the things you have to do. And I actually derive it for the beta distribution to show you these are functions. They are not, let's say, esoteric things, and they can be quite complicated. But notice, this is not a linear function of x. We just write down linear equations and hope for the best. And of course, the same applies here. This is a big mess. Now, is the beta distribution an esoteric distribution? No. Actually, if your data are percentages, don't use normality because you have numbers between 0 and 1. What's wrong with you? This is the distribution to look at. Can it be bell-shaped? Yes. And of course, later on in the book, I actually show a lot of these distributions and their curves. So let me just skip this and show you some functional forms. The normal is really straightforward. So you have straight lines,
It depends on, of course, the intercept, which is the beta 1 and the slope, but you can get all kinds of straight lines. However, the conditional variance is just constants. So it's just one number, and then you just assume that it doesn't really vary over X. Now, what I do here is to reverse X and Y and show you that these are different functions. Ironically, people in econometrics, they began worrying about linear regression in the 1930s. And they were flabbergasted to realize that these two functions can be very different. They actually wanted the betas and the alphas to be the same. Because theoretically, if you have a linear equation, you can solve the linear equation. You don't have a linear equation here. You have a distribution. So there are hundreds of papers asking themselves, why is it that these coefficients are not the ones we get by solving y and x like linear functions? 40 years. And you say, what's wrong with us? I mean, these are not linear functions. They come from something else. So here I show you that the intercept, the coefficients from the same joint distribution are quite different. So please don't get into those discussions. Some of the people doing these stupid things were from the London School of Economics, so there are some silly people everywhere. It's a prestigious university, but they were doing these stupid things as if there is a straightforward solution. Now, in the case of the normal, if we want to really understand what is going on, you need a bivariate distribution, bell shape. And of course, you don't want it to be too steep or fat tails. That gets you into trouble. And then if you slice it and then plot the contours, you get these wonderful ellipses, basically. Now, if they are circles, you're out of luck because X and Y are not related. There's no covariance. So you want these ellipses to be as squashed as possible. Now, what are the regression lines? Well, a lot of times in some of my presentations, I actually play a trick on people. So I actually draw X and Y and then give them a scatter plot. Yeah, it's an ellipse. And ask them to tell me what is the regression function. And you will be surprised. These are professors of economics, not students of economics. Almost all of them just tell me, this is it, the best fit. No, that isn't the thing. These are the two regressions. This is y on x, and this is x on y. Of course, they don't coincide, and you can't treat them as a linear equation. And if you have a scatter plot, that is never the linear regression. So you're going to see something like this and something like that. They all meet at one point, but that's the only thing they have in common. So be very careful. What we want is to use the data and replicate these things, because then we know what we are doing. We have the data, so we can just do that. But of course, you need to be really careful. All right. So terminology. I was always confused with the terminology in econometric textbooks. So I made it my problem to figure it out and make sure we know what we are talking about. So the regression is linear in X. That's one property. But it can be linear in parameters. Linear regression from the normal is both. You cannot have an X squared on the right-hand side. It's linear in the parameters and linear in X. That's important. Just calling it linearity really doesn't really cover it. And of course, this thing doesn't qualify. It's an X squared. What about this thing? Yeah, it's a square there as well. And of course, this is both non-linear in X and non-linear in the parameters. So be very careful how these things. So it has to be both. Now, the problem I had was mostly for the stochastic function. Because people in econometrics define homoscedasticity as, well, there is a constant there. Yeah, but what does it mean if there is no constant there? Well, I mean, what is the alternative? And of course, homoscedasticity, do I define it? Yes. This is heteroscedasticity. This is not the variance changes with the index. It changes with the X. When it changes with the T, you have heterogeneity, not heteroscedasticity, and the two are completely different. It's one thing that it changes with X, and a completely different thing, it changes with the index. What's the big difference? We observe X. T makes our task of estimating. There will be n different variances if they change with T. Now, can you find any textbook in econometrics where they make this difference? No. I published it in '86 in that green book. I find referees questioning some of what I'm doing, saying, but this is heteroscedasticity. No, it's heterogeneity. Heterogeneity has to do with whether the IIEd is valid. Homoscedasticity and heteroscedasticity has to do with the distribution. It's apples and sausages. So, just to make sure, here is a list of a ton of bivariate distributions for students who learn this material to realize how really special is the linear regression we teach in our courses. It's linear in parameters, linear in X, homoscedastic, and then you go very close. The next one, close to the normal, is the bivariate students. T, you get identical regression function. Identical. Even the parameterizations are identical. It turns out there is a whole family which has exactly the same regression as the normal. But what makes the normal in that family special? It's the only distribution that is also homoscedastic. Now, the same regression, the same parameterization, there's nothing really different. Look at the conditional variance as a function of the X in the case of the student's T. Seriously heteroscedastic. What is it? What is it? Well, it's a quadratic function of the mean deviations of the X's, and it has this degrees of freedom and everything else. What difference does that make? We cannot throw away the marginal distribution of X. Why? Because we need the mean of X, we need the variance of X, and they are not going to come out of the conditional distribution. Now, I learned that while I was a graduate student, and I was writing programs for the students on a mainframe using a very old language where I had to type everything on single cards. Every line was a different card. I had a pack of cards like this, and I go in the morning, basically delivering it to the mainframe, give it to the window, and I will go either in the afternoon or next day, get the results. I spent a whole week writing and rewriting the regression and scholastic functions and trying to estimate the students' T, and nothing happened. And then it dawned on me. At the end of that week, I'm missing something. There's no information that will actually estimate this mean and this variance that exists in the conditional distribution. I need to define, let's say, both the conditional and the marginal. In other words, I need to work with the joint distribution, not the conditional. I did it, it converged immediately. 3 years later, my supervisor with 2 other people published a paper on weak exogenality explaining exactly why it works. I just learned it the hard way. I wasn't quite sure what, but I knew it had something to do with where do I get the information to estimate those 2 parameters. The conditional doesn't have it. Now, if you go to Pearson type 2, this is the same family, exactly the same regression. They're all bell-shaped, by the way. But this is leptokurtic, this is platykurtic. That's why it's here. Also has a conditional or regression function, which is not homoscedastic. It's heteroscedastic, and it's also a quadratic function. And to estimate this, you really need to keep the marginal distribution. Your likelihood function is the product of the conditional and the margin. Then we go to the bivariate exponential. Everything falls apart. Linearity, this is a ratio of 2 polynomials. Homoscedasticity, this is crazy. These are 4th-degree polynomials, 2nd-degree polynomials. Go on to the bivariate Pareto. Linear regression? No. It's linear in X, but it's not linear in the parameters. Homoscedastic? Not in this world. Highly heteroscedastic. Then you go to the bivariate logistic. This is the only one which actually is homoscedastic, but its conditional variance is actually 1 number. So you don't have to estimate anything because it's just constant. And then you go, and you can see nothing resembles the regression function from the normal distribution. In the book, I have all of them. I will fit them into one. Sorry, that was a bad idea. Okay. So please look at them because it's very, very important to actually get the big picture so you don't fool yourself. And here are some of those regression functions and scholastic functions. So exponential, regression curves, logistic curves, they are very, very different. And if you have the correct scatter plot, you can actually spot a lot of this. So there are many different shapes. This is just to get you thinking that not all regression functions are the same, and of course, all scholastic functions are constant. And for a good cause, here I also have discrete distribution. You don't need continuous distributions to have regression. So I have bivariate binomial, bivariate Poisson. This is extremely important in many fields like medicine. They actually do have. And of course, negative binomial, as you can see, nothing resembles the normal linear homoscedastic world of the bivariate law. So be very careful. Now, I don't have subscripts in any of this. The reason is I can have contemporaneous or synchronic. I have X and Y dated at exactly the same time or temporal. When you have temporal, you cannot really condition on the observed value of the previous variable. You have to keep it as a random variable, and that's what this sigma is doing. This is the sigma field generated to retain its marginal distribution, not throw it away. So in dynamics, you have the whole sequence of conditional and marginal, and you have to be very careful. So these functions are the same. So if you go back, you can define dynamics or static models. They're always the same. So here we are. We want to decide which regression is actually appropriate for our data. What do we do? So the first thing we do is recognize that these are observations, pair of observations for X and Y, and you have to plot the t-plot. What is a t-plot? Well, what you do is you have xt or yt, t here, and this is your t-plot. So you can see all kinds of swings around, connect the dots, even if your distribution is not continuous, because you understand shapes. And those can tell you whether your marginal or the joint distribution you need to retain. So in chapter 5, I have all these plots. If you have IIEd data, which is what we are assuming here, it's very easy to see. There are no trends, there are no cycles, there are no crazy looking shifts, and you can immediately decide whether these are IIEd data. As I said, find me an IIEd data set in econometrics and I'll pay money. When people tell me IIEd is everywhere, I say, okay, show me one example and then we can talk about everywhere. There aren't any. Now, there are a lot of people who do cross-section. They say, I have cross-section data, I don't have to worry about IIEd. Yes, you do. The only difference between time series and cross-section data is in time series, there is a natural ordering, time. In your cross-section data, there might be 2 or 3 different. In the book, I have many examples. Every time you have cross-section data, you cannot define IIEd unless you have an ordering. That's how we define it. And there are many interesting orderings in cross-section data. If you miss it out, you make a mess of it. So people playing around with cross-section data don't know what they're doing. Scatter plot is the next one. If your data happen to be IIEd by some accident of fate, go to the scatter. What is a scatter plot? Well, you basically have X and Y on 2 axes, and then each dot is really a pair of values you see. In the seminar at 11, I'm going to show you the first scatter plot that established the Phillips curve. And it's a mess. So that was 1958. 70 years later, did anybody say, wait a minute, this data is not IIEd. You can't really view the shapes of the bivariate distribution if there is dependence in heterogeneity. Everybody just throws the scatter plot and then they go and connect the dots. It's lunacy. We know you don't have a bivariate distribution unless X and Y don't change over T. So each one of these comes from the same distribution. If the distribution is changing, how on earth is that the relevant plot? It isn't. And of course, you can see whether there is dependence and whether these two are related. So when I have X and Y, I see the contemporaneous dependence, if there is any. When I have yt and yt minus 1, I see the temporal dependence, if there is any. So it's very easy, if you have either of those, to actually pick it up in these scatter plots. These are practical things. They are not, let's say, theoretical or mathematical or anything else.
Aris,
Yes.
you can turn the page just at the screen. I mean, at the screen, you can move the pages
Ah,
by touching.
how do I do it?
Touch the
I go down.
at the screen.
I don't want to play with that. So I'll keep.
You can move.
Touch the.
Oh no, it's not.
On my screen, you mean?
Yeah, here, right here.
Okay.
That's it.
I just.
You can even drag.
That's okay. So here, I'm basically remind you of what is contour plots and scatter plots and how they relate to the different moments. And this provides the bridge between the probability theory part. This is all probability theory then. And the data. The data come in here. Why I didn't have any data up to this point. And I want to relate that to the mathematics, which is here probability theory. And here is how we do it. Oops, likewise, is something else here. You can take my list. Very good. If you are one of these very lucky people with IIEc data, that is how your y-t plot, your x-t plot would look like, and your scatter plot. Do you basically, if you see that, you are done. You are in good luck. Are you going to see that many times? No. So you have to learn how you can clean it up so you can have something you can deal with. So we can look at this and say, yes, that looks like that thing. So the regression is not going to be the principal axis, but it's going to be something, let's say, slightly up. And it doesn't look too bad. So what if your data look like that? Forget linear regression. Just forget it. What is the distribution? Well, look at the data. This data is clearly from a skew distribution because most of the observations around down here, and this dies out as you move out. That's your bivariate distribution. So a lot of textbooks on non-parametric statistics say, okay, my data look like this. This is impossible. So let's use a non-parametric. Come on. We have dozens of distributions. Yes, it comes from a bivariate exponential. What's wrong with you? What do? They just feed a line here, arbitrary line, and say, yeah, this is a non-parametric line. Lunacy. We know how these contour plots will give us regression lines, which are actually this variety. And then you go to the next one. This is your regression in that case. IIEc exponential. It's not the contours, but you can see it going through here and dying out. We have a functional form 3 pages before. We know what function to choose because we did the derivations. We just don't say, this is hopeless, let's just use non-parametrics and just find out an arbitrary function and call it a regression. You don't do that. These are the functions we are interested in. How do we just derive those by integrals. This is a continuous distribution or summations. And of course, I do a lot of those in the book. So look at them there, at least a dozen of them. This is just to show you a glimpse of what there is there. So, when can we throw away the marginal distribution? That was what I found the hard way, and 3 years later, or 4 years later, the three people I know very well, of course, at the LSE, they were working together, came up with the notion of weak exogenality. So what is it in sort of intuitive terms? Well, it has to do with this phi1 and phi2. They are what we call variation-free. In other words, they don't constrain each other. But we have to understand constraint is subtle. So here is the case of the linear regression that we're all familiar with, the normal distribution. And we know that these are the parameters of the conditional distribution. This is the phi1. These are the parameters of the marginal distribution. So what does it mean they are variation-free? It means we play a game. You choose these parameters, and then I check whether these parameters here are constrained. Constraint means their range of values changes. So, are there any people who dare play that game? Now, this has to be positive, of course, it's a variance. So think of any non-zero value positive you want to attach to that sigma 2, 1. All right. If I choose 1, would that 1 restrict the range of values of any of these? It's not going to constrain that because there is 1, but then these 2 change. So the range of values is not really anything you can play around with. Does it constrain this? Well, the this is a sigma 2. No, because this can take all positive values. Sigma 1, 2, we don't know what it is. So it doesn't. Here, well, it comes through beta, so it does not constrain them. What if we look at mu2? Let's call it 0, because it can be any value between -1 and +1. All right. This is not going to be affected. This is not going to be affected. Here, however, my mu2 is going to be 0. So this will disappear. But would that change the range of values of beta 0? No, because mu1 can take any values on the real line. This is what we exogenality. For these parameters here, constraining these, they're not affected. The range of values, which is really what we're going to be using for inference, is not constrained. But if we change the distribution, we can see it might get us into trouble. So, yes. So here is the case of a different distribution. The student's T. Oh, this is the normal. Where is my student's T? No, I just continue to do all of that and define the variation freeness. And here is a case where it doesn't really work. The distribution very close to the normal. So weak exogenality formally, it has to do with phi1, the parameters of the conditional distribution, not being constrained when you play games with the parameters of the marginal distribution. Formally, the parameters of interest are a function of phi1. So we are only interested in phi1. And of course, phi1 and phi2 are variation free. The three people is Engel, Henry, and Richard. I met all three. Henry, of course, was my supervisor for the thesis. The other two were collaborators, and they spent a lot of time at the LSE. So Here I play the same games and then immediately go to the regression next to the normal, which is the student's t. It has the same means, variances, but it also has another parameter we call the degrees of freedom. If mu is low, you have very peaked middle and fat tails. When the degrees of freedom is above 130, it will be difficult to distinguish between the normal and the student's t. That's for the univariate. But for the multivariate, it's always different. How? Well, we have already seen that. It's not homoscedastic. It's heteroscedastic. So even if we are interested in the parameters of the conditional distribution, which is also student's t, we cannot play games because we have these two and the sigma square, which is the same, but then we have u2 and sigma 2, 2. If we constrain those to 0 and 1, things fall apart. So, linear regression for the student's t has a heteroscedastic variance, but you also retain the marginal distribution of xt. So here I do the details to show you that yes, it doesn't work. But it doesn't work even in the case of the normality when you have temporal dependence. Now on that, the three people I just mentioned disagree with me, but that's fine. So what happens if x and y are yt and yt minus 1? This is what happens. So linear, yes. Homoscedastic, yes. But look at these parameters here. So if I'm interested in the regression parameters, and I can play games, restrict, in other words, mu and sigma 0, I can make a mess of these guys. What happens? Well, if I choose mu equals 0, this disappears. You stop there. You say, okay. What does it mean in terms of the regression function? Well, the regression function is no longer the observed value. So it's the expected value of yt given yt minus 1. But when you write it down and you get, let's say, coefficients, what do I use up there? I use alpha. So this function here is alpha 0 plus alpha 1 yt minus 1. You don't condition on the observed value, but the sigma field. So this is a random variable now. So you write it down with an error term, and it's both of them are stochastic. That's where the difficulty comes. You need the joint distribution, not the condition. And that's how I was able to call them out. So you don't have a well-defined joint distribution if you play the game, ignoring the marginal distribution. So here I show we exercise it doesn't work, and we have normality. So it's easy to suddenly get yourself into trouble for all of these. So here, again, I summarize the concept because it's non-trivial. You have to think about it. It has to be with constraining. And if the range of values of the original parameters doesn't change, when you constrain your marginal distribution parameters, then things work out. And here I explain, you really need the sigma field, not only for the regression function, but also for the stochastic function. And you keep the joint distribution. There's no other way to estimate all the unknown parameters for both of those functions. Do you need to go to the third and fourth conditional moments? No. And I have a paper where I show the third and fourth and fifth and so on are functions of the conditional variance. So Once you have the conditional variance, the rest don't matter. The reason it's symmetric, it's pear-shaped. But if it was skewed, that would not be the case. So here I remind you of all these functions. If, let's say, you can, the first thing that worried me, let me put it differently, once I discovered this, is do the functional forms change if I condition on the sigma field? And the answer was no. So all you derived before will be exactly the same, but your regression function now will have basically the capital Y. But the functional form is exactly the same. And that was really a comfort for me. I really worried that conditioning of the sigma field might change the functional form. It doesn't. And of course, now this is a random variable. It's not a function anymore, it's a random variable. It changes with, of course, this thing here. And to show you what happens, I go back to elementary examples just to get a feel of what does that mean in terms of conditioning and all of that. So here I have one example, and I show you what the sigma field looks like in terms of functions of Y. And here I have stochastic regressions. How are they different? Before, I had the values of X and the conditional means. Now, I need the probability of X for each different value here. That's the difference. I keep the probabilistic structure of X. So this regression function takes the value 0.387 when X equals 1 with probability 0.31. We didn't have that in the case of an ordinary conditioning. For value 2, the regression function is 0.902 with probability 0.41. So if you leave that out, you messed it up. It's no longer a stochastic function, as it should be if you don't have weakness regionality. And of course, we need to know how to handle this. It is a random variable relative to the Z sigma field. Random variables are defined with respect to, let's say, 3 pieces, if you remember correctly. Now that sigma field, the big one, becomes smaller, and it's the sigma field generated by Y. But everything else, this functional form is the same. Here, you have to be a bit more careful when you take the expectation of the conditional expectation. You really need the marginal distribution to do that expected value of the expected value. So here, I emphasize this. You need the marginal distribution of X. No way to lose that. And it would be the rule, not the exception. And of course, I remind you of what happens in the case of the student's T. Yes, real regression is linear, but that's a capital X. And it's a function here. So this is random as well. And of course, the parameters are exactly the same. But you have 2 extra ones, mu2 and sigma2. That was the thing that was going wrong with my likelihood function. I had only the likelihood function of the conditional distribution, not the right way to do it. And of course, there are properties. You're not going to remember any of this, but it's nice to remember how to manipulate this. So linearity means this E operator goes through constants and plus or minuses. That's the linearity part. The law of iterated expectation is very important. If I have this conditional mean and I want the mean of Y, I take another expectation using the marginal distribution of X. And so you're not going to remember it, but always remember there are these wonderful properties that we use a lot of times when we do regressions. And many more examples. So again, I want to show how you go from the joint distribution to the marginals, to the conditionals, and of course, how to derive the conditional moments and the unconditional moments if you have the conditional. You take another expectation just to show what is going on. And these two are extremely important properties. If I have the conditional variance and I want the unconditional variance of y, I need the conditional mean. You cannot do it without that. Take the variance of the conditional mean, the expectation of the conditional variance, and it gives you that. This, it took me forever to find. But I can see some textbooks now in medicine using that. It's non-trivial, and of course, it's expectation, covariances, and all that. But there is a way to recover the joint and the marginal moments from the conditional moments if you need to do that. Yeah, there are a few more examples, and here is really what you're assuming in the case of the linear regression. If you are a traditional econometrician, this is what you teach. And if you're me, you just laugh at this. As I said, fixed and repeated samples, what is that? How on earth is fixed? They're random variables. You are not doing experiments where you determine the value of X and then run the experiment. Why do we have these relics? Because we can't think straight. Again, no ambiguous variables. What the hell is that? Are we serious? I ran a silly regression and suddenly God came down and solved my problem. These are not serious things. You're not conditioning, you're just conditioning. You're not fixing X in the repeated samples because you don't do it for any other. And of course, this collinearity has to do with the data. This is a data problem. This is a problem of your theory. But you don't go to the theory unless you get the statistics right. If you have a well-specified model, which assumptions are fine, you can ask the question, is this other variable relevant? You bring it in, but you change the model. Do you retain the statistical adequacy you had before you brought it in? Now, if your model is already misspecified and you brought in variables, you're going to make a mess. And I have examples of this mess in the same textbook. So jump to the linear regression chapter. You will see examples of what can go wrong. If you don't get the statistics right and then worry about the theory, you're going to get a big mess. And of course, only these assumptions are relevant, but you have to basically transform them by doing this transferring, which if I can get it, yeah, here I'm showing you basically, you can make some sort of transfers. So you say, my error term is not quite an error term because it's conditional on X. That's fudging it, of course, because they attach the error and they're not thinking about X. But let's allow that. Yeah, this is equivalent to Y given X being normal. Of course, the zero becomes linearity in both the parameters and X. The sigma squared is a conditional variance of Y, not the error term. And of course, here, the uncorrelated. If you have normality, it means independent. So why do you pretend it's not independent? There's no other way. There's no other dependence if you have normality. But this is not a full set of assumptions about the observables. here I do the transition. But let me just go straight to what you will find. What is it you're assuming? You're assuming the conditional distribution is normal, that you can dig out of the error term. You assume linearity, homoscedasticity, independence, but you never really cared about the t variance. Now, some referees, when I started sending papers in, will look at it and say, no. We assume sigma squared is constant. No, you don't. You're assuming sigma squared is not a function of x, not a function of t. Of course, they go berserk, but that's bad luck. It's a completely different thing. Now, what happens if your parameters are changing with t? You don't have a model, you have a mess. Why? Because you have one parameter here that becomes n parameters. Another parameter here, another n. And another parameter, in other words, you have 3 times n unknown parameters. How on earth are you going to estimate 300 parameters with 100 observations? This is not a model. It's just a big mess. So that's extremely important. And when you want to judge the seriousness of each of these assumptions and its importance, you start from here and go up. This is the most important by a mile because it immediately makes your regression model non-existent, basically. Then the independence is extremely important. Then you worry about homoscedasticity, linearity, and normality. Actually, you don't worry about normality until every other assumption is valid. Why? Because the test of normality that are programmed in every package you can find tests, assume your data are IIEd. Of course, if they're not, that test of normality is invalid. So don't go for normality. Don't even go for linearity and homoscedasticity. Do these two and then start worrying about the rest. So this is really the important part for you to take really into account when you do practical things with data. You need to test all 4 or 5 assumptions before you do anything else. And of course, here I explain the difference between the error terms that we attach in the APP model and the difference with the error term here. The error term here has nothing to do with anything beyond the data and the particular stochastic process behind giving rise to the data. And by construction, this component here is orthogonal to the other component because u, t, is defined as the expected value yt given xt equals small xt, sorry, yt, I jumped minus that. That is the definition. It's derived. It doesn't have a life of its own. It exists because we are looking at y and its conditional mean as a function of the conditioning variable. Nothing to do with real variables or fixed and repeated samples or any of that jazz. Is constructed to be what it is and is data dependent. The minute I put another variable here is a different error term. Because the joint distribution now is 3-dimensional. Yt, x1, and x2. So median variables and all of that don't come into the statistics at this stage. Ask the statistics after you get yourself a statistically aggregate model. I'm going to leave you to read some of these and give you an example how easy it is to kind of fool yourself if you start with a model that came from their theory. So this is a very famous example that basically talks about the capital asset pricing model, which is extremely popular in financial econometrics. And well, I happened to come across a textbook by these two nice guys, IIEc, on financial econometrics. And they have the data at the end of the book and uploaded them in their website. I was fishing for that. So here is the data. They use that data to illustrate the cabinet. They decided, yeah, of course, it's brilliant. It's the foundation of pricing in financial econometrics. So, of course, they have many different data series. Today, I'm going to take only one. Excess returns in logs, of course, of Intel, and then excess returns of the market. And they define those in a number of different ways that you have to be careful. You need an interest rate that gives you really the excess returns beyond what you can get for sure if you have your money in a bank. So I allow them to do all of this. I don't want to get into it. And basically go straight to estimating their assumed model. They basically say the capital asset pricing model doesn't have a constant because the theory says it's zero. So what do they do to confirm the theory? They simply say, okay, we are going to put the zero there and then test whether it's zero or not. Now, they are oblivious to when you, let's say, put parameters, they change the meaning and all of that, but that's okay. So they think all you have to do here is estimate these two regressions and then find out whether the restriction is actually valid. There are hundreds of things wrong with this, but let's play along. So I take their data. Oops. Allow me to redo it. And basically use the data, estimate the regression. And of course, you do a t-test of the significance of the constant. And as it turns out, this is really very close to 0.025. So in their minds, this is okay. Why? Because they can choose the alpha any way they want. So suddenly, I want my theory to be valid. All I have to do is just say, okay, my alpha is 0.2. This is 0.024. Yeah. I'm in good company. Now, and of course, they go on to celebrate their success. This test, of course, depends on whether this is. Oh, I jumped ahead. Sorry, guys. This is actually important. So let me backtrack because, yes, oh, way ahead. So here we are. This is the original model. And this is where they do their t-test. And of course, this t-test is, let's say, non-significant for the 0.02 that they chose. The R-squared is not too bad. 64 observations, you have to be careful, of course. And then they want this to be significantly different from zero. And of course, they look at t-statistic of 8.4 and say, yeah, this is brilliant. Yeah, if the 5 assumptions you used are valid, you are a good company. But are they? The only thing you have to do is take the data and plot it. This thing here, and that thing there looks like IID. What's wrong with these guys? They never plotted that thing. What's wrong with it? Well, first, there is a trend which is non-linear. But that's not the only thing. Put the trend there. Just think of it. What is the variation here compared to the variation there after you take care of the trend? The variance here is twice as much as that. The same here. So you expect a linear regression model with that data to work? Yeah, if you never plot the data, you have no idea what you're doing. So, what's wrong with it? Everything. So let me go to the misspecification test. This is just to give you a glimpse. It's actually very easy. You want to test assumptions about the mean and the variance. Linearity is about the mean. Homoscedasticity is about the variance. Independence is about both. Constancy is about both. So you take the residuals, which is the closest you get to what is left after you do the estimation, and you basically start with the original regression. A constant and xt. For the conditional variance, of course, it's just a constant. That's the sigma square. But you start from the original specification. So these two have to be there because we're going to see whether they picked up all the systematic information. There's no information here. So how do we probe for the validity of different assumptions? Forget normality at this point. If everything else falls apart, you don't worry about normality. So, linear form, linearity. I can use xt squared. I can use the fitted value squared because you have both. The residuals and the fitted values, they're always available, even if you're doing non-parametric or you're doing, let's say, machine learning. So they can do a lot of these tests, but they choose not to. So this is a dummy variable for that shift. You saw peak, and then suddenly it changes. Trends, we know there is a trend there. It's a third-degree polynomial. You don't really need the t, but you need these two. And of course, because I don't have a lot of data, I don't want to use lagged y and x because I consume too many degrees of freedom. But lagged residuals would do it. So this is potential departure from 4, independence, potential departure from 5, which is the constancy of the parameters. They could be changing with the trend, and the shift. And of course, this is linearity. So we go to the conditional variance, the stochastic function. This is the original model, a constant. The same dummy, because it's the variance which just suddenly changes. But that, of course, affects the mean as well. Trends here, linear. Of course, this is heteroscedasticity, this is heterogeneity. That's why it relates to 5. And do these auxiliary regressions and do the tests. So, what passes? Only one, linearity. All the other assumptions are false. Do you test for normality? That's the last thing. It is normal because it's a big mess. Okay. So what happens if you probe for omitted variables? You start from a statistically specified model, and then you bring in another variable to say, is this potentially relevant? So I looked at the data set. This is Intel. So this is the 1970s. early 80s. And I looked at a big firm, which had nothing to do with Intel. It was before all the electronics came into cars. So I thought, General Motors, they have nothing to do with it. The others were kind of, and just to really make fun, like it once, just to make it completely crazy. You put it into a specified equation, surprise, surprise. It is statistically significant. It's 0.025, they assume this is 2.4. So what happens here? You're asking the village idiot a serious question. What do you get? A stupid answer. If you are going to do protein for omitted variables, start with a statistically aggregate model. Then you bring in your whatever potential variable. You don't do it, it's going to pick up your misspecifications. And here it's pretty obvious. I jumped so I don't give you the chance to guess. So this is their residuals. And you can see very clearly this big change here and there. There is the trend everywhere. You can see it in the residuals. And remember that non-linear trend that was missing? Yes, it's going to pick it up. Even if you put there my granny shoes, and I have run regressions with the number of shoes my granny used to keep interacting, just to show you can get all kinds of significant coefficients if you don't worry about statistical adequacy. So, what are you supposed to do? Well, get yourself a statistically adequate model. How do you do that? Well, pick up the dummy, make sure you have basically the trends so you can pick up what you left out, make it dynamic because you have cycles there very, very clearly. And then I show that this is statistically aggregate, throw in more general models accepting trends. What happens? Look at the p-value, 0.81. It was 0.024, remember? Now it's nowhere. Why? Because the model picked up all the systematic information. Then you bring in your potentially omitted variable. It isn't an omitted variable. It just picked up your misspecifications because it does have a trend. So even if that variable came out of Mars and it had a trend, quadratic will be significant. Not because it is, but because you made a mess of the statistical adequacy of the original model. And that's all I have. Any questions? Please feel free. Sure.
But I have a question. You said that with the linear model, we are assuming that X and Y are the relationship is linear. And then you...
If your joint is linear or not, then the dependence between them, it comes in the form of an regression function, which is linear.
What is that non-linear relationship?
You change the distribution.
Okay.
You can do a lot of things with linear regression. But even if I have other examples with financial data where the normal is actually a bad idea. And I estimate the distribution. It's still linear, but it's heterogeneous. And it makes a huge difference. I actually did publish a paper 40 years ago or something along those lines, basically about the efficient market hypothesis for which somebody got out their price. Right? His data. Estimated, did a good job with the specification, and ended up with a pseudo C. And each amount hypotheses. Nonsense. Now, did anybody take any notes? By the way, I used quite a few of their data sets, and they found out. So suddenly, they destroyed the data on their website because students were actually going there to show how inept their empirical examples are. And because in econometrics, there are empirical examples, but they never show you with that example is actually a valid example. So when I raised the question with these textbook writers, they said, we just wanted to show them numbers. Really? You wanted to give them some numbers that go with alpha, beta, gamma that mean absolutely nothing? Yeah, who cares? If I can publish without worrying about statistics, why would I spend my time testing the assumption? Please don't be that generation. These are, I don't even want to give them a okay. Do a good job. It's not rocket science. Yes.
Okay. Well, I have a question about economics. How to advise people that don't want to use mathematics or statistics to prove an economics argument? For example, sometimes they say that econometry is not useful, or sometimes they use arguments to prove that idea. I don't know what happened with them, but I believe that econometrics is useful. In this case,
if you want to put forward any theory about inflation, unemployment, whatever you're interested in, and show that this has substance, you need to do an empirical paper and say, the data support my case. And that's how economic theory changes. This afternoon or 11 o'clock, an hour from now, I'm going to take one of those examples. For those who did macroeconomics, there is a very fundamental relationship between unemployment and inflation. And they use data to change the original trade-off. They use expectations, and they use that, and then Friedman, and then rational expectations. And they were invoking data in support of their new theories. Do the data support these theories from 58 to 2025? None of them. They are all badly misspecified models like these guys. By example, because they were honest enough to put out their data. I had to find the original data, and that's extremely difficult. With Phillips, somebody got the data by looking at the scatter plot, because he dated the dots. And we can do that with a lot of history. For the Phillips curve, I spent years digging out these key papers together with the data. None of them even come close. So what do these theories that we learn in macro mean? Absolutely nothing. These are tales for 5-year-olds about the afterlife. They have nothing, they have no substance. So all these gurus who tell us about this economic policy will solve the stagflation and that it will, they're not based on anything but little stories without any empirical evidence at all. And I'm ashamed to say, what the hell is wrong with us? Those auxiliary regressions are difficult to do. My grandmother, if she was alive, could do it. You need Excel. You don't need sophisticated software. Excel would do it for you. You have to do some thinking what to put on the right-hand side, but here is basically feeding the data. You don't need a model there. You say, is my model basically okay? So use your imagination, put squares, put trends, put all kinds of things. Look at the data first, so you may get a guess. That's what is missing from econometrics. So you can imagine what happens when I send a paper. There is other people. I'm saying they're bozos. And you can imagine what happens.
Well, first of all, thank you for coming.
It's a great pleasure to be here.
And thank you for this wonderful presentation. I saw the other day in some logic course, phrase that said something like, in a strict sense, every model is incorrect, but some of them really work. So what I think we need in order for us to have a model that really works.
It comes from a sentence that a famous statistician mentioned. This is R.A. Fisher's son-in-law, George Box. In a few places, he says things like, all models are wrong, but some are useful. The problem is, people don't read the next part of the sentence. Because the next part of the sentence is, test your dumb assumptions. So I can always find quotations from people and attribute it to important people that I never really read. So I have several publications where I give the whole thing and say, stop the nonsense, please. No, all models are approximations of the reality I'm trying to understand. That's the whole point of statistics. But there are good approximations and lousy ones. We can distinguish between the two. And if we want to build a new theory, make sure we do a good job in proving that our assumptions we invoke to make our case, this is significant, this is large, this is small, are actually supported by the data. The only guardrail in empirical modeling is the data. There's nothing else. At the very least, we provide evidence that there is nothing else in that data that I didn't account for. For that data, we don't worry about bigger theories. But if we start with these models, and instead of changing the data and changing the story and going on and then saying I have more data and less data, let's start being serious. So when I was 25 or something, I wrote a paper. The future is the 50th paper. Because when I was taught, there are areas of macro, investment functions, consumption functions, inflation functions, unemployment functions, and I was really taken aback with the consumption function. I sort of looked at the data. It was really clear to me that these are not really serious papers, even though they're hundreds of. So I wrote a paper with the title, Revisiting the Empirical Consumption Function. Stylized facts or fiction? They had this, we know about consumption function, there are certain stylized facts, 1, 2, 3, 4, we all know them. So I took their data from different people who are making those and showed them. It's fiction. Now, it took 10 years to publish it, but eventually you get an editor who looks at the referee report and say, yeah, this referee is crazy, it's stupid things. Or he gives me a chance to make a good case for what I'm saying. That was the second one. I had a previous one on other things. But over the years, I have many, many different papers where I go back to the literature, replicate and show. We are now doing a good job. We're using empirical evidence for our theories. Our theories are made up stories. Thank you. Yes.
Thank you. I have a question. For example, just to be clear, so can we draw a linear regression in different shapes? I mean, like a curve, or it doesn't matter. So
Yeah, I mean,
it depends on the distribution of the depth.
yeah, the functional form could come from your theory. I don't dispute that for a second. But the minute you're going to start viewing your model as linear regression, you have to be aware of this list of different distributions that give you very different functional forms for the regression and stochastic functions. And there are dozens and dozens of them. Here. Sorry. Yes. So if you suspect your data don't come from a normal distribution, it means your linearity might be problematic. But here you have very different functional forms, each for a different bivariate distribution. And the list goes all the way down here. So make sure that when you do the data analysis, you see ellipses and all of that. If you don't, worry about linearity. So the scatter plots of these three are ellipses for all of them. But for the rest are all kinds of shapes.
Are the most common, no? The first three.
Yep. Okay, thank you guys for listening.
Tomorrow we will have the next class, the last one. It's with Dr. Spanos. He's coming also at a la misma hora. A las 8:09. A las 8:09 a la misma hora. Bien. Y sería la última clase. Bueno, gracias.
So you're the diehards, as they say. Pues sí, the presentation takes a particular area of applied econometrics, here macro, and takes you through from the original Phillips curve all the way to the current DSGE models, dynamic, stochastic, general equilibrium models. And basically tests the underlying probabilistic assumptions for all the various versions of the Phillips curve. Here is a list, because I had to leave out certain periods because I cannot talk for 4 hours. The paper is actually almost 40 pages. So, and it's a joint paper with one of my PhD students. So keep that in mind. If you have an advisor who knows the material, choose your applied area of interest, and just do that. Replicate and test the validity of these assumptions. I taught for 7 years, actually 8, at Berkeley College. We only had graduate students. And I had close to 50 graduate students. And I used to assign to each one of them a famous paper, always covering all the Nobel Prize winners and the big names. And their task, and that was the final project, which we count as 40% of the whole thing, replicate the data, test the assumptions, and if the probabilistic model is specified, re-specify to get a statistically aggregate model. You get 100%. Now, if you go further and relate it to theories, that would be a bonus. So I replicated during that period 50 times 7 pairs. And you can imagine, not a single one of them made it. That's why I knew very early in my career, and I decided, let's do a better job with the empirical evidence. So I will take you through. In certain parts, I will put more emphasis, and other parts, I will basically give no details. You can read the paper. Armando actually has a paper. So the Phillips curve began life in 1958 at the London School of Economics. So that was my interest right from the beginning. I didn't meet Phillips himself because he retired, but I did meet some of the other people from the LSE who got involved in this. And of course, it raised issues relating to the rates of inflation and unemployment, and went on to play a crucial role in policymaking because the shape of the curve offered a menu of choices between unemployment rates and inflation rates. But it sort of metastasized over the years. And usually, the excuse for changing the underlying theory was the data. But of course, if you don't do a good job with the data, why do you think the story is better? So that's the story this paper basically comes up with. And of course, there are many, many different confusions over the whole literature. So let's establish what we mean so we don't get confused, what we claim. What is an empirical relationship? An empirical relationship has to have two things. One, the underlying statistical model needs to be statistically aggregate. So the assumptions you impose on the data are actually valid. And then it has to be substantively adequate in the sense that it tells a story about actual macroeconomy. So you need both of those. But the first one is essential because you cannot go to the second one if you don't really have a statistically adequate model. So what I do is use another paper of mine. I've always been interested in physics and astronomy. And I knew the story how for centuries, the link between the sun and the planets was misunderstood. And of course, the first big theory about the relationship was actually proposed by a Greek king of Egypt, Ptolemy, or a relation to that king. And that was, there are circular, let's say, movements and circles on those circles, what we call epicycles. And that did okay and was used for navigation and many things until the 1600s, when a very famous astronomer, the best of his generation, Brahe, a Danish, collected the most beautiful, the most reliable observations for most planets, including Mars. But Mars was giving him a problem. He couldn't really figure out what was going on and gave the data to one of his assistants, Kepler. So Kepler spent 10 years care-fitting Brahe's data to get the circular motion of Mars around the sun. They had excellent data. The data are actually amazing looking at it back because there were no telescopes. Brahe was using a triangle at night to measure angles and distances and all that, and it's a miracle they ever got those nice numbers. So what happens in 10 years? Well, he fitted thousands of circles, and eventually it dawned on him that it wasn't a circle, it was actually an ellipse. And that's how suddenly astronomy changed. Now, for years, I wanted to find the original Kepler data. That's how you really do it. Because I was dying to find out whether the data are actually supportive of the ellipse that he fitted to the data. He didn't use modern methods. He just did the usual fitting. Okay? It took 25 years to find them. Eventually, I did. And of course, you can turn an ellipse into a linear equation using polar coordinates. So that was the easy part. And then I fit that equation, a linear regression, of course, and tested the 5 assumptions. It was perfect. Yeah, I mean, there were residuals, but all 5 assumptions were valid. Now, what did I have? I didn't have an empirical regularity. I had a statistical regularity. Yes, this shape, but there was no explanation, the substantive adequacy that I mentioned before. It took another 70 years or 60 something for Newton to come in and use a theory, his theory of universal gravitation, to explain and give the substantive meaning to the ellipse. This is how it works. Now, at that point, Kepler's heated equation or ellipse became a substantively and statistically adequate model. But there was a glitch, and this is something that is important in economics. When people try to replicate, after they understood that there is an explanation perfectly fine for all the other planets, and one of them didn't fit. However they tried, they couldn't fit. Let me just find it here. Well, this is basically the one closest to the sun. And part of Einstein's theory was to explain what that particular one, because the general relativity effects are actually very significant, didn't fit. So suddenly we knew it didn't change the result of Kepler and Newton, because it was really a good explanation, and the general relativity effects were tiny. They didn't make any difference. But for us, the lesson is, if we keep doing that, both statistical and substantive, expect the substantive to change. So there's nothing wrong with, this is the best theory we have supported with data so far. And we can live with that. But if the underlying statistical model is actually completely false, we just keep telling each other stories. And we pretend we actually know how to handle inflation and unemployment and trade-offs. We don't. And that's the story behind this particular relationship. So here is the Phillips curve. Let me just go straight to the scatter plot. This is from Phillips. This is how we dug out his original data, because he dated these dots. He just put a number there, 1951, 1956. And then we can use beautiful, let's say, scans, and he had the numbers here, the numbers there, so we can dig it out. So that happened many years ago, once the scanners came into being. He used data, the original period was actually something a bit strange. So he used annual data, UK, and they covered the period 53 observations, 1861, 1913. Now you might say they had data on unemployment and inflation. Yes, the British were good at that. So what he did basically was to look at that scatter plot and basically, because he had the dates, he basically created little circles all the way. So he had an observation there. You see that diamond? An observation here and then fitted the curve. Now, he was just curve fitting. He wasn't doing estimation the way we understand it today. So he had to do something else to prove that this is really real. So he fitted this curve with new data, 14 to 57. And he said, the goodness of fit is great. So here it is. Now, a warning. Goodness of fit, however you measure it, is neither necessary nor sufficient for statistical adequacy. So just because it fits well, it doesn't mean it's statistically meaningful as a relationship. So he came up with that strange looking equation. So what he did was to estimate, use those 5 things to estimate this part, this, and of course the coefficient for unemployment. He measured, of course, weight changes in a kind of funny way, and that's problematic. he was trying to basically improvise. So he would take yt plus 1 minus 1. So he left the thing in the middle and divided it by it. So it's kind of, and that's problematic. You don't go back and forth. But anyway, he created at least the first Phillips curve. And of course, when I sent it to referees, they say, but he didn't do any inference. I was forced to quote from Phillips. He was doing inference. He just did it in a kind of primitive way, which is fine, of course. So what's wrong with it before we start doing the analysis? As I said this morning, the scatter plot is meaningful as a picture of the joint distribution only in the case where you have IIEd data. Do you think this data, the way he averaged over yt and yt minus 1 and all of that, was IIEd? Who knows? But I plotted the data for the first time ever. Somebody actually plotted the data. So let's jump to that. It's a long way off, but here are the original data. What do you see? Cycles, irregular cycles. I mean, he tried to make a case that these are business cycles. But business cycles have to be regular. And these are not. The way they are spread out is up and down, and the distances don't match. But there is definitely dynamics that he missed out, and the whole fitting exercises actually. We knew. The minute I saw that, I knew, okay, we are done. I know that it's completely misspecified. But that will come later. This is just a warning. Don't use scatter plots. Yeah, if your data look like this, yeah, this is IIEd. They look like that with cycles. They have dependence. I had to do this for the referees because they never saw a plot. And I explained to them the presence of these irregular cycles is just positive dependence. It's nothing really, it's not regular enough to be anything else. So here we are. We start with the Phillips curve. It becomes very famous immediately. And the simple reason was that two very famous American econometricians, economists, Samuelson and Solow, both of them Nobel Prize winners, noticed it. And they did it for the United States. And they came up with very similar shapes. And suddenly it became an established empirical relationship. And that created a lot of buzz, two giants taking a paper from the LSE, and suddenly they're touting Islam or its importance. So it changed shapes and forms and all of that over the years. And every time every decade, we go into different functional forms and different that and different the other. In the 70s, we had the short run versus the long run. There is trade-off in the short run, but the long run is vertical. I mean, all kinds of things based on data. They are invoking data to make their case, and all of these guys. And then in the 90s, we had non-accelerating inflation and unemployment and the Great Depression through, let's say, a spanner in the works. And suddenly they say, well, we're not quite sure, but it didn't die. DSG models have their own, let's say. So this is a long story, but we tell it in the summary, and in the paper, of course, there is more. So to shed light on the recurring controversies, I visit with the student influential papers with a twofold objective. First, to bring out the fact that these controversies have been theory-driven. And somebody else actually published a paper saying they have nothing to do with the data. They're just different stories, not supported by the data, but he never really checked the data. The validation of the probabilistic assumptions invoked by the estimated models has not been an issue in this controversy. Nobody really said your model is actually useless. Second, to challenge the conventional wisdom related to the Phillips curve being an empirical relationship. Remember, both statistically aggregate and there is an explanation, substantively aggregate, that fits. By showing none of the cited papers is statistically aggregate, rendering the trustworthiness endemic. So here I sort of make a case that goodness of faith really doesn't tell you anything at all, because the very measure of goodness of faith assumes the validity of your assumption. For those who did regression, the R square is completely nonsensical if you don't have IIEc type data. And if you look at the formula, you can see immediately why that happens. So seemingly statistically significant coefficients and fabulous stories really don't make a case. Now, why didn't anybody try that? Of course, I did most of it many years ago, but I wanted a good student to dig some of the more recent data so we can actually tell the story. And the reason is we are simply very non-serious when it comes to data. So here is a famous textbook on BSG models. Canova was one of the editors that turned down my paper on BSG models, so I decided to call from him. So how does he explain when in my paper I replicated dozens of these and none of them came in close? He says, BSG models are misspecified in the sense that they are in general too simple to capture the complex probabilistic nature of the data. Really? There are three kinds of assumptions. Three, not 15, not 7. Distribution, dependence, and heterogeneity. You need all three, nothing else. So suddenly became, this is a jungle. And it says, hence, it may be fruitless to compare their outcomes with the data. Really? So what are we doing with empirical modeling? We are comparing the results with our shoes, or what is it we're doing? He says, both academic economists and policymakers use these BSG models to tell stories. So it doesn't matter that the stories have nothing to do with the data. We tell good stories about how the economy responds to unexpected movements in the exogenous variable. If you don't have a statistically aggregate model, how on earth do you do that? What you estimated there is not a real relation. It's a made-up relationship. He says that in a sort of straight face. Never mind that whether the stories have some link to the phenomenon of interest. We're not really talking about economists. We're just playing around game. And of course, that gave rise to the particular data. Aren't we really interested in what gave rise to this data? Curve-fitted BSG models invariably misrepresent and finesse the information in the data. And I have two different papers. Their data replicate, showing that they have nothing to do with the data. Now, this guy, Forger, he's criticizing the theories, but he's hinting that the theories have nothing to do with the data. So I offered that part to confirm exactly what he said. So let's look at this over, or at least the top papers in different periods to see what goes wrong. Now, this is basically a kind of setup, background story, which I talked about both yesterday and today in the lecture. So this is not totally new to all of you. And it relates to what makes data confirm or deny theories. And here I start with the basic, the traditional APP, a priori postulated models that usually come from theory. That's the statistical, and of course, I explain the differences. The statistical have to do with the probabilistic structure of the data, nothing else. And for every APP model, you need to find a set of assumptions, not 50,000, 3. Distribution, dependence, heterogeneity. IID means only the distribution matters. You need all 3 to confirm or affirm the structure of your equation with an error term at the end. You need to do that by unveiling the implicit statistical model. If you have that, then you have something to talk about. Confirm or deny the validity of your statistical model, and then proceed to do whatever you want. Now, where I had difficulty for the last 50 years was that there are 2 complementary perspectives in empirical model. The one is this APP that comes with theoretical information, your theories, macro here. The other comes from the data. And what matters for the reliability of your inference and the trustworthiness of the ensuing evidence are the assumptions you impose on the observable process, because that's the link to the data. Error terms don't link to the data. The probabilistic structure of the observable process is directly related to the data. The data is one realization of that process. Univariate, multivariate, that's what really matters. And of course, you need to dig it out. What is this model? It's the joint distribution. This is what all of statistics and statistical inference depends on. It's not the joint distribution of the errors. It's the joint distribution of the observables. You have to dig it out. And of course, it also relates to your model, but it might have different thetas, the different parameters, and differences in specifications. But you need to do that. And as I say, 3 categories, not complex and many different things. And I'm going to repeat myself. I showed that in the presentation in the morning. This is really the most important formula in statistical inference. Yes, it's ugly. It takes 10 minutes to explain it, but that's what we do when we start with linear regression, estimate the coefficients and say the coefficient of beta 0 hat is normal. The coefficient of that is chi-square. The t-test or the test of significance is t and so on. All these sampling distributions come from here. Exactly the same joint distribution of the sample with 2 caveats. When you derive this, you assume 2 things. This distribution satisfies Kolmogorov's existence theorem, that is probabilistically valid. And this says the assumptions are valid for your data, not somebody else's data. That is statistical adequacy. You need both. Because if you don't have a well-defined probabilistically joint distribution, everything will go wrong. So this is really where everything basically comes together. How we do it? Well, all statistics, let's say estimators, test statistics, predictors, whatever we use, is a function of this sample. Whatever function is, linear, quadratic, cubic, whatever it is. And we are integrating over those events relating to that functional form, but we have always the same joint distribution. Now, what is going to happen if we made a mistake, either probabilistically there's no well-defined distribution, or some of your assumptions are invalid, hell will break loose. So, what happens there? Well, if this thing here is invalid, which is your statistical model, basically, either of those will destroy your inference, because this will be erroneous, your likelihood function will be erroneous, which means your sampling distributions up here are going to be erroneous. What are the consequences? Well, nothing will actually stand to. It's going to distort those distributions. It's going to give you non-optimal inference procedures. So you have excellent estimators when your assumptions are valid. Your assumptions are not valid. You cannot claim. This OLS is actually the best blue or yellow, whatever it is that we tell stories. And of course, in addition to that, this invalidity of this induces huge discrepancies between the nominal error probabilities you derived, assuming validity, and the ones with your data, which are invalid. So if you're doing testing and you use 5% significance level, but either of those two conditions is false, your actual type 1 error could easily be 0.9 or 100%, and can very easily happen. I have simulations where I play God, and you can see a tiny trend, 0.1 t, makes a 5% into a 97% with 100 observations. And the worst part of it is, all those people with large data sets, they feel comfortable because my error increases, so I can invoke asymptotics. You shouldn't. Because that departure from the presence of the trend or dependence gets worse and worse as n increases. So as n increases is not your comfort. If you have an IID data, yeah, it's comforting, but not for this thing. It becomes worse and worse. And of course, that's where the reliability of inference goes through the window, and you're mucking around with t-tests and other tests, and of course, they mean absolutely nothing. So you have to relate it. So I use phi and theta with your model, and you can actually test any additional assumptions that your theory brings into the picture. So that's important to remember. We can actually improve the theory, not just the statistics. And of course, here I talk about identification, but I'm not. And then remind you of what we usually do when we specify the linear regressions. Assumptions about error terms, and then bring in irrelevant, simultaneity, and all kinds of nonsense. This has nothing to do with probabilistic assumptions. This is theoretical. Do a good job with that. Don't worry about this. So instead of confusing everybody and ourselves, let's separate it. And of course, I do it here for the linear regression. You saw it this morning. You basically start with normal IID, go to the conditional distribution. If you have normality, you are in good shape. And of course, since you have only two variables, talk about covariances, a bivariate type distribution will work. And those are the assumptions you're making. Here I have the multivariate X, so we don't think that there is something magical about the two variable case. It works for any number. And you have normality, linearity, homoscedasticity, independence, the most important being constancy of the parameters. None of those models ever pass that. So if your parameters are changing with t, you don't really have a model. Period. So, and as a bonus, of course, we get these statistical parameterizations, which are extremely important to understand what you're estimating. You're not estimating a Phillips curve. You're estimating means, variances, and covariances shuffled around. They become a substantive relationship only after you test those assumptions and they are fine. Not before. So don't rush to it. And of course, something which is important here, I impose assumptions of Z, and then the certain assumptions are directly related to one assumption here, which is 1, 2, and 3. Normality, linearity, homoscedasticity had to do with the joint distribution being normal, which means you have to be very careful here. So when you reject one of the three, say, wait a minute, is the normality the problem? Or the linearity, or the homoscedasticity, and then find a way to interpret your results. And of course, the other two are straightforward. I have several papers which I explain that these assumptions on the Z process are this close to being necessary and sufficient. In the case of the dynamic model, they are necessary and sufficient. And of course, testing your assumptions. You don't need specialized software. You need Excel. Run the regression, take the residuals and the fitted values, and you can do wonderful things. So, the residuals, there are good reasons why we have the residuals. Your equation here starts with the original model. You can actually have Y here, but the residuals are better. So, the original model, but that basically says this is what I captured, the information I captured. And then you put generic terms, trends, lags, shifts, and all of that, that you don't need other variables with the data you have. So if I want to test whether assumption 5, which says my coefficients are constant, I put a trend in. Doesn't have to be this trend. You can use other trends. You can use squares and all of that. And if you look at the data, it's the surest way you're finding out. This is for the nonlinearity in the x's, not the variables. This is for, let's say, the dependence, temporal dependence in this particular case. Here, I have both, instead of left residuals, I have both of them raw there. I want to see exactly whether both of them are important. And then you test the significance of these two together for the regression function. Now, the regression function is affected by two, the linearity, the independence, and also the constancy of the parameters. Then you take the residual squared, which represent basically the conditional variance, and your model is constant. Remember, it was sigma squared. Then you do the same thing for the assumptions that relate to the conditional variance. One is constancy of the parameters. Sigma squared is constant. This is heteroscedasticity. So this is heterogeneity. This is heteroscedasticity. That's where econometricians get confused. And of course, this is basically temporal dependence. But because the left-hand side is the square, it won't be a very good idea to use raw xt minus 1. You square them because these are always positive, and you try to have something which is meaningful. This is all you need to do. And you'll be surprised what you can learn by these very simple Excel type auxiliary regressions. So what happens if you reject some of these, let's say, assumptions? You don't go there and start mucking around with that assumption. Because remember, normality, linearity, homoscedasticity come from exactly the same source, the normality of the Z. So there is this gray area you have to navigate, but it's not, again, rocket science. So you're going to figure out how you can actually improve your model by respecifying it. Here, you're not looking for a model. You're looking for ways that your model can be wrong. It doesn't matter whether you put another lag we don't need or another trend that you don't need. If you have tons of data, do that. Here, for most of these, especially the original data, I'm a bit stingy on throwing too many variables on the right-hand side, but it's a sort of an exploratory exercise. You want to learn what systematic information you did not account for, and then use that to re-specify. So misspecification testing is not using the data twice, kind of nonsense that I had to face early in my career. All kinds of excuses not to test the assumption. But you looked at the data. Yeah. When I look at the data, they change their structure. Oh, yes, at the beginning, it was crazy. Oh, you can't. You're cheating. Yes, because my data have certain systematic information which is going to be there whether I look at them for a day or a week or 10 years. It's something that is inherent. So don't be afraid to reply to those kinds of nonsense. And many others, because I published papers, many papers explaining that this is really pathetic. So if you want to see what's going on, these are the two plots you need at this stage, which is if you have IID data, do a static regression. The regression in the case of Phillips was non-linear, but non-linear in logs. So it was, in parameters, it was really linear in that sense. But if you have cycles without lags, you can't really do it. And in the case of the data he had, as I said, these are the raw data. Nobody ever thought of it. The minute I did, I knew we're in for many surprises. I don't blame Phillips, of course. 58, we didn't even understand regression at the time. So I blame everybody else afterwards. And of course, I need this to figure out exactly what is going to be wrong. And the cycles have to do with dependence. So I'm expecting problems there. That's how you should see it. So I repeat again, what happens if you have lags? And it's the same thing. You just expand the linear regression into the dynamic linear regression. So I'm going to skip a lot of those things and go to evaluating the fitted curve. Now, the first time I did it, I basically said, look, guys, if you have the original data, you have everything you need. They said, but there is only one variable on the right-hand side. I said, doesn't matter. That's sufficient. Actually, you need the fitted values and the residuals. The rest, you can improvise. So for the data scientists here and the machine learners, you can do misspecification testing. All you need is the residuals and the residuals squares, and and the fitted values. So this is the estimated equation. He never really gave any standard errors. He just kept fitted. But he's doing statistics. He went on to infer the statistical evidence in sections 2 to 4 seems to, in general, to support the hypothesis stated in section 1, that the rate of change of money wage rates can be explained by the level of unemployment and the rate of change of unemployment. So I quoted that. I didn't want to do it. The referee said he never really did any. Of course he did. Now, the next guy from the LSE took the data and did real regression. That is Bill Lipsey, whom I knew because as an undergraduate, I used his textbook in economics as a basic textbook. But he already left, so I couldn't really. And of course, we have someone saying his findings are remarkable, even if one disagrees with his interpretations. So they said, yeah, the empirical evidence is straightforward. We might not agree completely with his interpretations, but that's okay. So here is very simple auxiliary regressions. And you can immediately see the significance of a lot of these coefficients here. And I have a table, of course, where all of these are. The tablet that is completely specified. Functional forms, the whole thing. So Lipsy comes in 1960, 2 years later, very, very soon afterwards, a colleague, and he basically said, no, it's linear regression, but these are not linear parameters. So that's fine. He doesn't have to find a joint distribution or any of that. This is too early. But we can still do specification testing. So he fitted actually 2 or 3 different forms. He did very little with the specification, if anything at all. And of course, here are the 2 most, let's say, widely used afterwards. And as you can see from the auxiliary regressions, of course, I have the, let's go straight there. These are simple regressions, as you can see. This is Phillips failing 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. Anything below 0.05 is bad ideas. Can you specify? Yes, but the way he defined the variables with WT plus 1 and minus 1 messes up the dynamics, and you have to unscramble those. So you have to redefine what was going on. This is messing up the temporal dependence, and you can't really find anything. Let's say any model that we actually cover. So this is the first period, Phillips and Lipsy. Then we have Samuelson and Solo. They actually fitted these curves, and then we have half a dozen other people, Klein and Ball. These are famous names, by the way. These are not your pattern variety. And we actually were able to get their data. It was easier for them. And of course, we replicated all of this. I'm not going to sort of give you all the results because we're going to be here for another 4 hours if I do that. And of course, the person who taught me econometrics was this guy, Dennis Sargon. And he actually estimated one of these equations. And when I was still an undergraduate, another professor sent me to his office, and I got the original data and replicated his estimated equation. And he asked me to test the assumption. And one of the assumptions was false. So I waited for weeks before I had the temerity, as we say, to walk into, I was an undergrad, to walk into his office and say, one of your assumptions is false. But eventually he called me and said, come on. And he didn't really, he says, wonderful, re-specify it and come back and sit. I did, and of course, I continued to become an econometrician. At that point, I was 50-50 between mathematical economics and econometrics. This really did the trick. So, testing the validity of these assumptions, comparing different specifications of models for model purposes and all of that, we do that in the paper. And the closest anybody came to a statistically adequate model was Dennis Sargon in 1964, because he had the courage to put lags and trends. What happened when he published this 1964 paper? All hell broke loose and said, you idiot, the theory doesn't say you need trends and lags, and you're not following the theory. And that's when I was doing my PhD, and I said, yeah, you're confusing statistical models with theoretical models. You don't need permission from your theory to capture the regularities in your data. You start with the theory specification, test the assumptions, re-specify, account for the regularities. Yes, you need lags to capture those cycles. Actually, there is a trend as well. The only thing wrong here is the functional form. So here are the estimated equations. The other things, and he was very close. So this was the closest to a real empirical relationship. And of course, here are his results. This is the part that really I knew as an undergraduate what to do with it, and it was easy to specify. And of course, we replicate many other models, including Perry for the United States, the same period. And as you can see, there are problems everywhere in all of this. So that's the next period. Here is the Perry thing. He did all kinds of silly things with the dynamics. And of course, it turns out to be a big mess. Now, I leave one period out because it's a long story. But I want to go into this GMM and IV because that's another horror story. I mean, the first time I was taught this stuff was basically, here I have an equation, but xt is correlated with the error term I have never seen. How the hell is that story? What does it mean? Well, it's correlated. And why is index 2 correlated? Well, it's uncorrelated. With the error term, nobody has ever seen. And then we want estimators that account for this and that. Not even magicians do that. Uncorrelated and correlated with something we can never see. And then we make stories and IV and GMM and all of that nonsense. So I put all those in a formal joint distribution and explain that these are gimmicks. If there is correlation, it's not the error terms, it's the observables. Where we have a statistical model with real assumptions we can actually test. That was 35, 40 years ago. But publishing this took at least 2 decades. Because suddenly people were feeling uncomfortable that they are making assumptions about error terms they have never seen. You don't need any of that. You just have a joint distribution, all the observables, and then you figure out what are the assumptions and so on. So I'm going to skip this because it's a big issue, but I take care of all of that. This is the statistical model, basically. This is y and x. This is linear, of course, and it's simple. And of course, all of this is statistical, and we also have not only the assumptions, but also the relationship between the theory, which is the phi's, the theory parameters, and the statistical parameters. And we can test what we call these over-identified restrictions. I can tell you from now that it fails up here. But even if you get a statistically aggregate model here, this often fall apart. And I did it for many DSG models, not just 1 or 2, more than a dozen. So these instrumental variables and all that are completely unnecessary. Once I have this, I have the joint distribution of the sample. Nothing else matters. The likelihood function is just a variation of that. Maximum likelihood, do we do it? Forget GMM and IV and WX and so on. They're gimmicks. Based on what? Statements like this. X1 is correlated, but X2 is not. On what basis do you make those assumptions? Feel like. And you tested this? No. You don't have error terms. You have residuals, but the residuals implicitly have the model you estimate. They are not the same as the error terms. Their sampling distribution is actually very different. So don't play those games. Find out what the statistical model is and figure out what's going on. So what are the papers we're replicating here? Well, Galli and Gibler, very famous paper, and Galli again with several people improved the model. and it had a lot of impact on this particular literature with the Phillips curve. And of course, they had expectations and all of that. But here is what happens to their theories when you test them. Zeros, zeros, zeros. And here, of course, they have a ton of data. So in a sense, they should decrease, let's say, the alpha to compensate for, let's say, 2,000, sometimes 200, and so on. Phillips had 30-something before, 42 observations. These people have a ton. And of course, it's helpful for somebody who is testing their assumptions. And as you can see, this instrument set is a big mess. And of course, the other one is not better. Again, full of holes. And of course, here are the conclusions. There are 10 other papers being replicated and having the same problems. A retrospective view of the empirical literature of the Phillips curve over the last 6 decades shows that none of the influential studies is found to be statistically adequate, not a single one, rendering their empirical evidence untrustworthy and undermining the fabulous theory-driven stories. Everybody has just wonderful stories to tell. They're not based on the data. They're just made up stories. Empirical evidence in econometrics ignores this key role of the data as the only fender, the only thing that can stop you from making a fool of yourself. Against unsubstantiated claims regarding learning from data. You learn absolutely nothing. Of course, it didn't stop any of these guys telling the stories. So, this leaves no room for evaluating the substantive value. What substantive value is? If the statistical, let's say, specification is full of holes, the estimators are meaningless, your tests are meaningless, so what are we going to do? Now, in other papers with the DSG, I actually respecify and tell them what they need to do with their theories to get them to actually come very close to the statistically adequate model. But here, it was too long anyway. And we did try, and for most of these data sets, we were able to get statistically adequate models. So it wasn't that there were none. There was none for Phillips and Perry, because they were both playing these games with the dependence. But for all the others, we could actually get statistically adequate models. So, not only the traditional economic narrative of the Phillips curve is questionable, that's the point made by Feder, but the empirical trustworthiness of the studies upon which these stories is basically equally questionable. That is, the Phillips curve is yet to be pertinently evidenced as an empirical relationship, both statistically and substantively adequate. Now, is there anything we can do? Yes. The onus is on applied mathematicians to provide sufficient evidence. When they send me an applied paper, I'm looking for misspecification. If you don't provide me with that, I don't believe a word. Now, can you imagine if journals employ that strategy? You send a paper in and with a nice story and fabulous t-statistics and all of that, and says, show me the evidence that you have a statistically adequate model, and I'll send it to referees. If you cannot do that, please keep it in your living room. Frame it if you want. Where is the substance? If that happens, I mean, this small change, suddenly we will have reliable things to talk about and disagree, theories competing, but on the right basis. Without it, it's just my story and your story, and neither has anything to do with the evidence coming from the data. And of course, the traditional error fixing shortcuts, and there are hundreds of them. almost every regression package prints out the Darby-Watson test. Now, the Darby-Watson test is a bad test for temporal dependence, but it doesn't say anything about error correlation. So when you have a bad Darby-Watson, you don't cure the problem by saying, my error term is not IID, it's first order autoregressive. Even if it was third order autoregressive, it will reject the null. So in a misspecification test, you get hints that your original assumptions about X and Y are false. Not the error term needs to be beautified and do all kinds of things. And there are hundreds of these. Heteroscedasticity, consistent standard errors. Do they do anything to make sure that the actual error probabilities are very close to the nominal ones? Nothing. And I have thousands of simulations to show you. Absolutely nothing. You have to do the specification on the observable, not the error term. That's always a bad idea. So don't believe any of those. And of course, that brings out these journal editors. Yeah, we can teach econometrics this way, and we all do our misspecification testing. But we send it to a journal who doesn't care. A lot of times I had the journal editor say, take out this. It has nothing to do with the substance. And of course I refused. I don't publish it. I want to show that what the assumptions I made are actually valid. This is the evidence. We might disagree about the tests, but on the whole, if we show our auxiliary regressions, we are very close to deciding what is true and what is false about the assumptions we use. So it's going to take not only the way we teach and learn econometrics, the way we practice econometrics, but also these guys with the journals. They don't want evidence. They want a good story that goes with a few numbers and some apparent large p-values or small p-values and silly things like that. We are not going to do anything better. Now, is this the situation with the Phillips curve only? No. Every applied area I ever worked in gives you exactly the same picture. We don't know what we're doing, but we are good storytellers. And we gave Nobel Prizes left, right, and center on good empirical evidence that never was. So we need to get our act together. So I feel passionately, and I'll come back if you want me to. Please don't waste your time learning nonsense. Instrumental variables and GMM and two-state least squares. Get the joint distribution of the sample and you're done. The maximum likelihood estimate is 100 times better than anything else you can bring there. Don't play games with error terms. Go back to that horrible looking formula with the integrals. Remind yourself that if you have a probabilistically specified joint distribution of the sample, and that's what the unit root literature was built on, 7 million citations. 7 million, imagine that. Or any of your assumptions are invalid for your data, you're cooked. Easy to check. Do it. Respecify. Even change your theory in light of the new evidence. But we are going to learn from data only if we do that and provide sufficient evidence so we can believe each other. As it happens, I don't believe a word in any applied paper I ever came across. There's no evidence that the assumptions upon which all of these were built are anywhere near being valid. I don't think I have anything else here, just in case. No, that's it. So, questions? I said an hour. I went just a bit longer. So any questions? Please feel free, challenge me. Yes.
What happens when you transform the data to adjust to some kind of assumptions on your model? Like sometimes you don't have normally like, I don't know, linearity, but you adjust it to like have some kind of data that can be.
There's no problem with transformations of the data. None. As long as they're meaningful. And once you transform the data from levels to logs, you get the statistically adequate model. Remember, the logs is a non-linear equation, but it's still an equation. And you would be surprised if you look at, as I have, thousands and thousands of papers. Most are log linear, not linear. And there is a reason for that. But that's for another segment. So don't be afraid. If you need to transform the original variables, but keep them meaningful, go for it. But don't apply some crazy transformation that you will have a hard time giving it a substantive, meaningful relationship. Yes.
So, Professor, we need to do the test. We need to test the errors or the original data. Because when we, for example, if we put in the model trend, then we split the trend from the errors, and then
we have to, let's start with the theory. You have a relationship.
Mm-hmm.
The error is what you left out and many other things.
Mm-hmm.
That's not what you should be worrying for the statistical aspects of the model.
Mm-hmm.
You unveil the implicit assumptions about the observables.
Mm-hmm.
Once you have that, you have the statistical model. Mm-hmm. There are assumptions about X, Y, and Z. You have data, you can easily test those. You need to have a complete set. Errors are never complete sets of assumptions. So once you get there and you have a specified model, don't be afraid to re-specify, even though your theory says there are no lags or trends, like Sargan did in 1964. My whole thesis was about we don't need permission from your theory to capture the regularities in the data. Without it, we cannot say anything. But we separate the two. So don't be afraid. Put lags, put trends, put shifts. Get a statistically adequate model and go back to your economic theory. Okay, why is the theory not explaining the presence of this? Now, for when you have trends, it's excellent for statistical inference. They do the job. But for substantive significance, a trend is ignorance. Something is happening there. It's creating this shape, if you like. So in tomorrow's lecture, I'm going to tell you what happens. If you really need to put trends there, but you need a substantively meaningful model, you have to replace it. And there are clever ways to do it and stupid ways to do it. And I'll tell you the clever ones.
So in most of the econometric studies, people, when they want to publish, they define what they call the identification strategy of causal relationships. And when you work with that, you need to work with, for example, instrumental variables, discontinuities, clean shocks, all that stuff.
As long as you can translate those things into statistical terms, you can do all of that. So when I was a student, the big deal in econometrics was what we call the simultaneous equations, where you start with a structural model. The theory gives you 7 equations, a lot of zeros and all that. And then we basically told ourselves that we have to identify those structural parameters. So what we are going to do is solve that to a reduced form, estimate the reduced form, and test the zeros, what we call the over-identified restrictions. What's wrong with it? Everything. That reduced form is your implicit statistical model. It has 5 strong assumptions. If any of those are invalid, you're identifying your structural parameters relative to some imaginary reduced form, and nothing to do with the data. So that is the implicit statistical model. Has all the assumptions, re-specify if you have to, put lags, put trend, don't be afraid. Capture the regularities, and then start talking about identifying the structural parameters. Because you have a chance there to test the zeros. But your test will be real, reliable tests. If you start with specify a reduced form, the whole thing falls apart. So that was one of the few papers I was able to publish 40 years ago, because I used a data set, which was used by many, many different other people, and showed that the reduced form was completely misspecified. I respecified it, and then said, identification is not going to work for you. And I was forced by the referees to name names. I try to avoid that, because when you call somebody out, they usually get very miffed. So I had 2 citations where the referees forced me to write 6. It was a very popular data set for the French banking system. So there were quite a lot of papers. So I just chose the most cited papers for that period. And one of them was one of my friends. He wouldn't speak to me after that. That's what happens. People get miffed. Did he criticize other people all the time? The fact that I included one of his papers in a list of papers, if I use this data and they abused it, basically, that was enough for him to say that. Okay, our operation is done. So there are, let's say, negative side effects from all of this. I did lose a few friends like that. But most of the scientists, they say, okay, what can I say? I disagree with you, so fine. You can disagree and we can still be friends. Other questions?
Professor, what about Bayesian econometrics? I mean, they go to the program from the start. I mean,
I have a real problem. So, as it happens, I clashed majorly with Bayesian econometricians. When I started, Jean-François Richard, one of the 3 in that extensionality paper, was actually extremely helpful. And I never really had a fight with him. The problem I have is that to start the thing going, you definitely need a statistical model, as we do. You need a distribution, joint distribution of the sample, as we do. You need a likelihood function, as we do. So it's basically L of theta, the data Z here, proportional to that. But of course, instead of generic Z, we have zeros. And this is now a function of theta. This is all fine. When I told them that they have to test this, they say, no, we don't need to do that. Why? Because we have a prior distribution on theta. So they have a pi of theta, a prior distribution, and that will solve the misspecification problems. How? You are assigning probabilities to different values of theta. How on earth? These are statistical parameters. There are means, variances, and covariances. How on earth do you have any previous information so you can attach probabilities? And of course, when I have macro models, this is 30 different parameters. How do I specify 30 multivariate distribution for the known parameters that I don't observe, and they have nothing to do with the data. You see, this comes from my, whatever it is, I have extraterrestrial abilities. They have a problem. So what do? They say, well, we need to order these figures and use conditional distributions, which are univariate. Hey, you want me to believe that? So I have positive distributions, like this variable, this theta takes positive values. I'm going to use normal. I mean, if that's fine, minus infinity plus infinity. I'm going to use some other distribution doesn't fit. Well, we have this objective. And of course, the guy with the objectives and I nearly came to punches in a restaurant in his town. He wouldn't allow me to finish what I was doing. Not about Bayesian statistics. It was frequency statistics. He just interrupted me every second. And to avoid him, when we went to the restaurant, I sat at the other end of because I knew he was a test. He came and asked to change with somebody else. And he gave me the usual stories which I heard 50,000 times before. What's wrong with frequencies and what's good for Bayesian statistics. And of course, I couldn't really stay silent. So at some point, I used a very special example, simple, normal IID. And he got so furious because some of his students were sitting behind him that he stood up to punch me. I mean, I said, they're going to throw us out. Do you want a fight? We'll be outside. Kicked through the door. He was frothing in the mouth. That's it. We met many times in conferences. I don't even say hi, he doesn't say hi. We are both happy. So there are problems. Where do you get this? Where do you get the loss functions? Where do you get all of these other things? And why don't you care that this thing has assumptions you can test? I have issues with that.
What they say is that they estimate those sampling according to the distribution they find from their priors and things like that.
Yeah, I mean, what they're doing is simulating. So in the quotation I had in the previous presentation, they basically simulate these integrals that they need to get the posterior.
So they say, I don't need a test because I simulate, I obtain a sample.
But simulating means you assume some structure for the observables now. You can't really fake it now. It's all the observables. They seem to be happy just play games. Sorry.
Yes, thank you.
I see all kinds of problems.
What happens if we don't have, well, my question is, what happens to our model if the data we collect is far from exact? For example, when we use GDP, the data in that set is open in process. For example, if we are making some political economic model and we extract the data from the GDP, and the GDP has no exactly measured, what happened with our model?
That's a terrible. So another thing that I said in many talks was, when we estimate the demand, do we really have the right data? Our theory comes out of optimization. Anything that comes out of an optimization refers to intentions corresponding to the different range of prices we were faced, and so on, and ceteris paribus and all of that. What do we have usually? Quantities transacted and the prices, the actual prices. How do we relate what actually happened to consumer intentions based on an optimization? Do we really think we are estimating demand functions or supply functions? We not. I wrote a paper 50 years ago. And I said, look at this. We are estimating adjustment equations. Yes, there are demand and supply functions behind, but it's an adjustment equation. And it's the dynamics we're going to capture. So don't fool ourselves. In other words, the thing we take out in theory, it is this optimier and all of that, it's the only thing we can actually estimate. And that goes in many different fields. In macro, they have these optimizing representative agents, and they think the published data is what they want to estimate. So that's another tier of knowledge. I got into it very early, but I realized initially. In my thesis, I actually have empirical examples of demand and supply, and concluding we are estimating adjustment price and quantity adjustment equation. I left it on one side. I had many other files to find, so that was one of those. I said, okay, too many. But let's think about it. I did the cross and then say, wait, what happens if the price is here? And it's really, if there is a way to guide you, it's adjustment equations. How do we, let's say, bring the demand and supply together and trends to go in one direction or another and so on? If there's a story there, it's one of those topics. I had enough enemies, so I don't need all these series chasing me around.
So, any applied economist now has access to unprecedented level of data, computing power, different types of models, and so forth. But you've already said that it's not really solving this issue. No? It might be actually exacerbating them because we have the capability of doing much more data analysis than before. So you mentioned that like fundamental statistics is a way to kind of avoid this problem, but I was wondering the role of theory.
No, the theory begins to enter the picture really once you get the statistics. You start with the theory to begin with. How do you choose the relevant variables? Why do you have X and Y's separate? You must start from somewhere. That's the a priori postulated model. Stick an error at the end. I don't have a problem. Make as many assumptions as you want. But dig out what those assumptions and your functional form imply about the observable process. I actually unveiled all these models in books and papers, so you don't have to do any work. I did it for the whole profession. I showed how you can do the test, the specification test, joint tests, because if you don't have joint tests, you're going to get into trouble. Tomorrow, I'm going to give you an example how you get into trouble. Then you have something meaningful statistically. Go back to your theory and say, why isn't my theory explaining these lags, this trend, this something? Think about it. If you have a trend in statistics, it's fine because your error probabilities are what they are, what you think they are. The actual, the nominal are fine, so you can do testing. But it's not statistically meaningful. It's ignorance. So the first thing to think is, am I missing some key variables? Now I'm going to do it with real data and basically say, let's think about it. So I choose 3 potentially relevant additional variables. And I justify my choice. I start with the statistically aggregate model, and my task is if I put these variables in, the trend should go out. If I want to a substantive explanation, and that's why. Bring them in, suddenly the T is insignificant, and then I go on to explain how the statistical model can now be framed in terms of, let's say, theoretically meaningful adjustment process. That's most of our models are adjustment processes.
Professor, are ignorance also?
There are occasions where I won't be able to get rid of the T. But this was consumer's expenditure, and I thought, okay, I have disposable income, I have price level. Are there anything else that play as income or as part of this money illusion? And I came up with 3 variables. Of course, I started with 5 or 6, but then eventually trimmed them down and tried them all. And these 3 got rid of the trend. And now I don't have variables when I aside from the substantive. But if I didn't have the statistical model to begin with, that exercise is exercise in futility. It's not really meaningful because you start with a meaningless batch of numbers. And as I did this morning with Kaben, yeah, you can put a variable to pick up the trend, but that doesn't mean it's meaningful. Other question?
I have a question. What do you feel about spatial econometrics? Most of the models in spatial econometrics are related with the error term. And well, I got the idea that you can relate with something that you can see because the error term is.
Great question. I have 5 friends in this area. I could even name them. Pesaran, Baltaji, and 2 or 3 others. And I began worrying about this thing 20 years ago. Because as you say, they are modeling the error terms. And they pile one assumption upon the other because they have a fundamental problem. How do, or what kind of ordering do you choose for your spatial? I made suggestions because geographers know how to do that. Suggestions about all kinds of other things. You need an ordering to talk about anything. They refused. They want the error term to do all the rounding around. I still have those suggestions in papers. There are plenty of ways to do it. I mean, geographers turn 3-dimensional map into 1-dimensional ordering. And it's actually better than time. So what you do is define dependence and heterogeneity, because without it, you cannot really define it. Then you have something to talk about. Get rid of the errors, unveil the implicit statistical models in terms of the 3 categories: distribution, dependence, heterogeneity. The last 2 need an ordering, meaningful ordering, which will define the rest. They refuse to do it. So they have 15 assumptions about the error term. You really don't observe it, so you can assume whatever you like.
So is the same for the regulations with individual? Because I feel it's the same.
I'm always flabbergasted when I discuss these things. When I say, you cannot define IID because you need an ordering to talk about conditioning and all of that. Conditional distributions. You cannot do it. But they say, okay, but I have a wonderful error term. I can assume it's correlated with that and correlated with the other. And I say, yeah. But that doesn't make you a cook or a chef. What you're doing is knocking around with silly numbers. So Professor and I will have screaming matches. With Baltaji, we left less of it, but I was teaching at Cambridge once a week, and every lunchtime he was there, so he and I could fight it out. Thanks for listening, guys.